Previously, we had taken a look at uniform circular motion, and we were mostly interested in the horizontal plane. Now, let's take a look at what happens if we have motion in the vertical plane. Here, the difference is instead of just having one force, be it a tension or gravity or whatever, being what is providing our centripetal force, we'll have multiple forces acting in the radial direction, either working with each other or working against each other. So we'll start by taking a look at a roller coaster. Let's say one like this. And what I want to look at is right here where the car is right at the top of doing our loop-de-loop. So there we go. So right here, our car is going at some speed v, but let's go and take a look at the forces acting on the car. So we will always have the force of gravity acting down, and we'll also have a normal force acting down. And in fact, the normal force can't point up in normal operating circumstances. And this is because if we look at the track and we got the wheels here, the normal force can only push down on the wheels like this, perpendicular to the track. And in fact, you'll see in real world cars, there'll actually be a secondary pair of wheels, that, usually much smaller, attached like this, so that should you get into a situation where you actually need these wheels, you could have a normal force pointing up. But of course, when you engineer the roller coaster, you don't ever want to have to use these safety wheels here. And so in normal operation, the normal force will only ever be pointed down at the very tippy top of the roller coaster. So you can go ahead and say that Fr is equal to ma sub r. And here, this will be the force of gravity plus the normal force. They are both pointing in the plus r direction. And we've seen that a sub r is equal to v squared over r. Force of gravity is mg. So this actually gives us a minimum speed that we have to travel, we have to go at to get over this. We divide both sides of the equation through by m. We'll have v squared over r equals g plus the normal force over the mass of the car. And if we multiply through by r and take the square root, we will have that the speed of the roller coaster at the very tippy top will be r times the quantity g plus n over m, like so. Now, the smallest n can be is 0. Because otherwise, without the safety wheels, what would happen is you would be detached from the track, and in fact, you'd be moving in a parabola, which could be very exciting, but would also probably be pretty lawsuit-inducing. So we don't want that. So our minimum speed will be when the normal force is 0, but that will just be root rg, which is our friend the critical speed that we saw from before. So in order for a roller coaster to maintain contact on a loop-de-loop, at the top, it has to be going at least as fast as our critical speed, root rg. All right. So we can go ahead and flip this one around and think instead of a roller coaster, let's think of a car going over the crest of a hill. So there's our car. Now here, same deal. It's going like so. And if we draw a free body diagram for our car, we'll see here that we have the force of gravity acting down, but now we have the normal force acting up, and it can never point downward. This is because it can only point, because that would be trying to somehow attract the car to the surface, and that's not something the normal force does. So what about here? Well, again, if we go set up our RTZ coordinates, we see that this would be the plus r direction because that'd be directed to the center of the curve. And so if we take the r component of Newton's second law, we'll have the force of gravity now minus the normal force would be equal to our mv squared over r from before. So same deal. And now we can figure out what our maximum speed is before we lose contact with the ground and go flying off in a parabola off the edge of the hill. So again, dividing both sides through by m, we'll have v squared over r is equal to g minus n over m. And we can rearrange that to get that v is equal to the square root of r times g minus n over m. Well, the way we make this bigger is to make the normal force less and less. But again, the smallest n can be is 0. So our fastest speed, we can go over the hill and still stay connected to it, would be r times g, square root of r times g, which is again our friend the critical speed. Thus why it's a critical speed. In the case of the roller coaster, it was the slowest we dare go over to stay attached. Here, it's the fastest we can go over and stay attached. Alrighty. So in the next video, we will take a brief look at non-uniform circular motion. We'll see you over there.